ring definition, a non-empty set capital R with two binary operations. So first binary operation is addition. The second binary operation is multiplication. So a non-empty set capital R with two binary operations R comma dot is said to be a ring. It satisfies the following conditions. For all a comma b comma c belongs to R. So a comma b comma c belongs to R. So first condition of ring R comma plus is abelian group. So R comma plus is abelian group is nothing but so abelian conditions. R comma plus is abelian group. So abelian group is nothing but so first condition closure with respect to addition. So R comma plus is closed with respect to addition. So second condition is associative condition. So this is second condition. A plus B plus C equals to A plus B plus C. So first condition is closure. Second condition is associative. A plus B plus C equals to A plus B plus C. So next third condition identity. So with respect to addition, addition of identity is 0. Addition of identity is 0. Here, then there exists 0 in capital R. So 0 element is nothing but 0 is the identity element with respect to addition. So 0 in capital R such that A plus 0 is equals to A, that is equals to 0 plus A for all A belongs to R. So this is the condition for identity. So A plus 0 is equals to A plus 0 is equals to A or 0 plus A is equals to A. So this is the condition for identity with respect to addition. Addition of identity is always 0. So next fourth condition. So next condition is inverse. So every non-zero element for any A belongs to R, there exists an element minus A belongs to R. So every A belongs to R, so minus A belongs to R such that A plus of minus A is equals to 0. That is equals to minus A plus A. So addition of identity A minus A is equals to 0. So this is inverse condition. Inverse of A is minus A. So minus A inverse is A with respect to addition. So this is nothing but addition of identity is 0. So in case identity element is does not exist, identity element is does not exist. So inverse also does not exist. So therefore R comma plus is not a group. Okay. So first condition closure, second condition associative condition, so next condition identity, so next condition inverse. So these four conditions closure, associative, identity, inverse. So these four conditions are called R comma plus is group. So group is nothing but it satisfies four conditions. First condition closure, associative, identity, inverse. So then we can say that R comma plus is a group. So next, fourth condition, last condition, A plus B is equals to B plus A. So A plus B is equals to B plus A is nothing but commutative condition or abelian condition. So commutative or abelian condition. So condition is nothing but A plus B is equals to B plus A. So this is commutative condition. So these five conditions so first condition closure, associative, identity, inverse, commutative. So then we can say that R comma plus is abelian group. R comma plus is abelian group is nothing but it satisfies five conditions. So next to the second condition, R comma dot is semi group. R comma dot is semi group. So semi group is nothing but it satisfies only two conditions. So first condition is abelian. First condition is closure condition. So second condition is associative. So with respect to multiplication, with respect to multiplication, first condition is closure. A dot B belongs to R. For all A comma B belongs to R, so that implies A dot B belongs to R. So this is first condition of semigroup. The second condition, for all A comma B comma C belongs to R. For all A comma B comma C belongs to R, that implies A dot B dot C is equals to A dot B dot C. So like this, A dot B dot C equals to so next associative condition with respect to multiplication. A dot B dot C is equals to A dot of B dot C. So this is associative condition with respect to multiplication. So first one closure, the second one associative condition. So ring is nothing but R comma plus is abelian group. So second condition, R comma dot is semi group and distributive laws. So left distributive law and right distributive law. So these are the 5 conditions. So first one, R comma plus is abelian group, R comma dot is semi group, left distributive law, right distributive law. So then we can say that R comma plus comma dot is a ring. Okay? So this is definition for ring. So 8th chapter, ideals and homomorphisms. So first ideal definition. A non-empty set capital A of a ring capital R is called a ring, is called a ideal. So ideal is nothing but it satisfies 2 conditions. So first condition, A comma A1 comma A2 belongs to capital A. So that implies A1 minus A2 belongs to A. So ideal first condition, A1 comma A2 belongs to capital A. So that implies A1 minus A2 belongs to A. So this is first condition of ideal. So I'm here. So second condition. So left ideal and right ideal. So A into R. So A into R belongs to capital A and R into A belongs to capital A. So this is left ideal and right ideal. So if R is right side, we can say that right ideal. If R is left side of A, we can say that left ideal. So ideal definition, first condition, A1 comma A2 belongs to capital A. So that implies A1 minus A2 belongs to capital A. So this is first condition of ideal. Second condition, A into R belongs to capital A. In bracket lo chudandi okkasari, R into A. So R into A belongs to capital A. For all A belongs to capital A and R belongs to R. For all A belongs to A and R belongs to R. So this is the condition for ideal. So left ideal and right ideal. If capital A is said to be a ideal, so then there exist both left ideal exist and right ideal also. Both ideals are exist. Left ideal and right ideal. So this is the definition for ideal. So yeah, clear. Here also same definition. A non-empty set capital A of a ring is called ideal if A1 comma A2 belongs to capital A implies A1 minus A2 belongs to capital A. The second condition, A belongs to capital A and R belongs to capital R. That implies A into R belongs to A and R into A belongs to capital A. So this is the definition for ideal 8.3.2. The definition of ideal. So this is also same. 8.3.1 also same. The next example. In the ring of integers Z, every subgroup Z comma plus is an ideal for let capital A is subring capital A is subgroup of Z comma plus and A belongs to A comma R belongs to Z, then A into R is equals to A1 plus up to A if R greater than 0. So if R is equals to 0, so all are zeros. 0, 0, 0, 0. So that is equals to if R less than 0, negative, minus A, minus A, minus A. So therefore, in each case, A into R belongs to A, hence A is an ideal of Z. Okay. So A is nothing but A is subgroup of Z comma plus. A is subgroup of Z comma plus and Z is ring of integers. So this is the example. Next definition. Let R be a ring and S is a subring of R. The intersection I such that I is an ideal of R and S subset R is equals to I is called ideal is generated by S. It is denoted by S. So this is the generated definition generated by S and it is denoted by S. Note that S is the smallest ideal. So S is smallest ideal of R containing S. So this is generated by some elements. If S is generated by A, connotation here, S is generated by A, then we simply write A generator of A or generator of A. These are the pronunciation generators. So S is generated by A. So this is definition for smallest ideal of S. So next operations on ideals. Let R be a ring and A comma B two ideals of R, then the sum of two ideals, A plus B of A and B, it is denoted by A plus B. So the first element is belongs to A and the second element is belongs to B. So this is the addition of sum of two ideals. A plus B is equals to A plus B such that A belongs to A and B belongs to B. Okay. Next. So next factor ring or quotient ring. So factor ring or quotient ring is nothing but R by U. R by U. So R is a ring and U is ideal. R is a ring and U is ideal. So definition, consider the cosets in a ring corresponding to an ideal of a ring. Let U be an ideal of R comma plus comma dot. Then clearly U is a subgroup of R comma plus. Since R comma plus is commutative group, U is normal subgroup of R comma plus. Then we can introduce another binary operation and on the quotient ring R by U, and in the following theorem we can see R by U comma plus comma dot is a ring. So R by U is nothing but factor ring. So factor ring or quotient ring in R by U, R by U, R is a ring, R is a ring, U is ideal. Okay, U is ideal. Every element in R by U, every element in R by U is of the form coset form. So like this, A plus U, okay, comma B plus U. So every element in R by U is of the form A plus U comma B plus U. So like coset's form, okay? Left coset, A plus U comma B plus U. So this is factor ring. So next homomorphism definition. Homomorphism definition: a mapping pi from a ring R into R dash. A mapping pi from a ring R into R dash is said to be a homomorphism if pi of A plus B is equals to pi of A plus pi of B, and pi of A into B is equals to pi of A into pi of B for all A comma B belongs to R. Okay? So homomorphism conditions. So first condition, pi of A plus B is equals to pi of A plus pi of B. Pi is a function. Here pi is a function defined. Pi is a function defined from R to R dash. Okay. Pi is a function defined from R to R dash. So we can observe here domain and codomain. So domain and codomain both are different. R comma R to R dash. In case a pi is a function from R to R, so domain and codomain, so these two are equal, then we can say that isomorphism. So homomorphism definition is nothing but it satisfies 1 1, pi is 1 1, pi satisfies 1 1 condition and onto condition, pi satisfies 1 1 onto and homomorphism condition. Okay. So isomorphism definition: a pi is a function from R to R itself. Pi is 1 1 function, pi is onto function, and pi is homomorphism. So then we can say that pi is isomorphism. So isomorphism definition is nothing but a pi is a function defined on itself. So pi is a function defined on itself, R to R. So but homomorphism is nothing but pi is a function from R to R dash. So different domain, different codomain. So pi is 1 1 and onto. So clearly a 1 1 homomorphism is called monomorphism, and and onto homomorphism is called epimorphism, and bijective homomorphism is called isomorphism. A homomorphism from a ring R into itself is called endomorphism, and an isomorphism of R onto itself is called automorphism. Two rings R and R dash is said to be a isomorphic to each other. It is denoted by R isomorphic to R dash. So the number of definitions ఉన్నాయి ఇక్కడ. So 1 1 homomorphism. So 1 1 homomorphism is called monomorphism. So monomorphism definition is nothing but it satisfies 1 1 condition. So monomorphism is nothing but it satisfies 1 1 condition and homomorphism condition. Okay, na? So monomorphism is nothing but a pi function R to R dash. A pi function R to R dash is said to be a monomorphism.
Give me one example, sir, please.
Is said to be a monomorphism. Pi satisfies is said to be a monomorphism. Pi satisfies 1 1 condition and pi satisfies homomorphism condition. So then we can say that pi is called monomorphism. So first condition. So next to epimorphism. So epimorphism definition. So epimorphism is nothing but, so first one, pi is onto. So pi is onto and homomorphism. So epimorphism is nothing but pi satisfies onto condition and pi is homomorphism. So then we can homomorphism. So like, so this is surjective and injective. So 1 1 is another name is injective. So onto another name is surjective. You know. So monomorphism is nothing but homomorphism and 1 1 condition. So epimorphism is nothing but onto condition 9 homomorphism. So these two conditions are satisfied. Then we can say that pi is called epimorphism. Okay. And bijective homomorphism is called, so bijective homomorphism is called isomorphism. So bijective homomorphism is nothing but, so bijective is nothing but it satisfies one condition onto condition. So bijective is nothing but one and onto. So isomorphism is nothing but one onto homomorphism. So isomorphism is nothing but pi satisfies one condition, pi satisfies onto condition. So pi satisfies homomorphism condition. Then we can say that pi is isomorphism. And continuation, a homomorphism from a ring R into itself is called endomorphism. So a homomorphism from a ring R into itself. So like this, pi is defined from R to, pi is defined from R to R. So defined itself, pi is function R to R. So defined itself is called endomorphism. A homomorphism from a ring R into R dash, R into itself, R into itself is called endomorphism. Okay. So next continuation, isomorphism of R on onto itself is called automorphism. So automorphism is nothing but onto isomorphism. So onto isomorphism is called automorphism. So two rings R comma R dash is said to be isomorphic to each other. So it is denoted by R is isomorphic to R dash. R is isomorphic to R dash. So this is notation for isomorphism. So R is isomorphic to R dash. So these are the definitions of homomorphisms. So here number of definitions are there. First definition is homomorphism definition. Pi of A plus B is equals to pi of A plus pi of B. Pi of A into B is equals to pi of A into pi of B. So next to monomorphism definition is nothing but pi is homomorphism I 1 1. Injective or 1 1. So then we can say that pi is monomorphism. So surjective or bijective, surjective or onto. So epimorphism is nothing but pi satisfies onto conditional homomorphism. So then we can say that pi is epimorphism. So bijective homomorphism is called isomorphism. So bijective is nothing but 1 onto and homomorphism. It satisfies three conditions: 1 condition, onto condition, homomorphism. So then we can say that pi is isomorphism. So endomorphism is nothing. Endomorphism definition: a homomorphism from a ring R into itself. R into itself is nothing but domain and codomain. So domain a function, pi function R to R. So pi domain and codomain are same and it satisfies 1 condition, onto condition, homomorphism condition. So then we can say that endomorphism and an isomorphism onto itself. Onto isomorphism is called automorphism, and it is denoted by R is isomorphic to R dash. So these are the definitions of homomorphism of a rings. So if pi is homomorphism of a ring R into R dash, then pi of 0 is equals to 0 dash, where 0 comma 0 and 0 dash are the 0 elements in R and R dash respectively. So here pi of 0 is equals to 0 is nothing but every identity element in domain can be mapped to identity element in codomain. Like, so this is R, so this is R dash, 0 element, here 0 element. So mapping is pi. Okay. So R comma pi is a function of R to R dash. So pi is a function of R to R dash, and so zero element in R can be mapped to zero element in R dash. So this is zero element identity element with respect to addition in R. So this is also zero element is the identity element with respect to addition in R dash. Every identity element in domain can be mapped to identity element in codomain. So therefore pi of 0 is equal to 0 dash. First condition. So next condition, pi of minus a is equals to minus pi of a for all a belongs to R. So pi of minus a is equals to pi of minus pi of a for all a belongs to R. So next third condition, pi of a minus b is equals to pi of a minus pi of b for all a comma b belongs to R. So this is third condition of, so this theorem proof no need. So next kernel definition. Kernel definition. If pi is a homomorphism from R into R dash, then kernel pi. So kernel pi is denoted by kernel pi is the set of elements A belongs to R such that pi of A is equals to 0 dash. Pi of A is equals to 0 dash. The zero element of R dash. That is kernel pi is equals to A belongs to R such that pi of A is equals to 0. So kernel pi definition. So kernel pi is equals to, so this is condition. So kernel pi is equals to A belongs to R such that pi of A is equals to 0. So here pi is a function from, so pi is a function from, so kernel pi definition. So pi is a function from R to R dash. Pi is a homomorphism of R to R dash. Then the kernel pi is denoted by kernel pi. The set of elements A belongs to R is nothing but domain element such that pi of A is equals to 0 dash is the zero element of R. So so pi is a function from R to R dash. So domain elements, so domain elements are A, B, C, and codomain elements 0, 1, 2, 3 up to so on. So this is pi is a function from R to R dash, and so kernel pi is nothing but, so kernel pi is nothing but A image is 0, C image is 1, B image is 0. A image is 0, B image also 0, C image is 1. So kernel pi is nothing but which elements in domain. So which elements in domain can be mapped to 0 elements in codomain. So which elements in domain A comma B are the elements in domain R. So A comma B are elements in domain are mapped to 0 element in codomain. So the set, so kernel pi is nothing but here only two elements because so a comma b are mapping to 0. So pi of a is equals to 0. So this is function. Pi of a is equals to 0. Pi of b is equals to 0. So therefore a comma b r belongs to kernel pi because images of a and b are zeros. So A comma B are mapping to 0 elements in codomain. So then we can say that pi of A is equals to 0, pi of B is equals to 0. So therefore A comma B. So these two elements are belongs to kernel pi. So kernel pi is nothing but which elements in domain can be mapped to identity element in codomain or 0 element in codomain. So then we can say that those elements are belongs to kernel pi. So but here
Sir,
each
in
mapping,
case, yeah.
In case of addition, 0, but multiplication 1, right?
Yes, addition of identity is 0.
Identity. Yeah, okay.
Identity is 0. So multiplication
Yeah.
of identity is 1. So but here we are taking r comma plus. So r comma plus is the r comma plus is abelian group.
Is the ring. Okay.
Yeah, so that's why. So we are taking here A is mapping to 0 element time, B is mapping to 0 element. So here 0 is the identity element with respect to addition. So 0 is the identity element with respect to addition. So that's why we are taking identity element in R dash. So 0 is the identity element in R dash. Okay. So this is the definition for kernel pi. So kernel pi, so definition is nothing but which elements in domain. So which elements in domain can be mapped to identity element in codomain with respect to addition only. Yeah, definition is nothing but pi
Yeah,
of
got
a
it.
is equals to, yeah, pi of a is equals to 0. So that's why. So which elements in domain can be mapped to 0 element in codomain? Is clear? So this is the definition once again. Pi is a homomorphism from R to R dash. Then the kernel pi is denoted by pi. Kernel pi is the set of elements A belongs to R. Is nothing but. So which elements in domain? So which elements in domain? So these like 1 comma 2. So which elements in A belongs to R such that pi of A is equals to 0 dash. So definition here, pi of A is equals to 0 dash. The 0 element of R dash, that is kernel pi is equals to A belongs to R such that pi of A is equals to 0 dash. Okay. So 0 dash is nothing but the 0 element or identity element in domain. So this is the definition of kernel pi. So theorem, next theorem. So this is a very, very important theorem. Fundamental theorem of homomorphism of a rings. So before going to this theorem, so very, very most important theorem, fundamental statement to fundamental theorem of homomorphism of a rings. Before going to this theorem, yes. Theorem 8.6.8. Let pi function R to R dash be a homomorphism of rings, then kernel pi is ideal of R. So we have to show that kernel pi is ideal of R. So ideal definition. So before going to this one, let pi function R to R dash. So your domain and codomain are different. R to R dash be a homomorphism of rings. So pi satisfies homomorphism condition. Homomorphism condition is nothing but pi of a plus b is equals to pi of a plus pi of b, and pi of a into b is equals to pi of a into pi of b. Is clear? Pi's homomorphism is nothing but it satisfies two conditions. Pi of a plus b is equals to pi of a plus pi of b, and also second condition, pi of a into b is equals to pi of a into pi of b. So clearly pi's homomorphism of a rings is given. So next, then we have to show that kernel pi is ideal of R. So kernel pi is ideal. We have to show that kernel pi is ideal of R. So ideal definition. We have to prove that kernel pi is ideal. So ideal definition. So first condition is first condition of ideal a1 minus a2 belongs to a. So this is first condition of ideal. So next second condition, a into r or r into a. And so these are also belongs to capital A. So ideal definition, a1 minus a2 belongs to a. So first condition of ideal, a1 minus a2 belongs to a. And so second condition of ideal, r into a and a into r. Left ideal and right ideal also belongs to a. So both exist, both ideals. Left ideal exist equally and right ideal also. Is clear? So this is the ideal definition. And kernel pi. So kernel pi before definition, previous definition, kernel pi is equals to a belongs to R such that pi of a is equals to 0 dash. Okay. So here theorem is given. pi is homomorphism, and we have to show that kernel pi is ideal of R. You know, prove since pi of 0 is equals to 0 dash. We know that every every zero element in domain can be mapped to zero element in codomain. So this is the first condition. Pi of 0 is equals to 0 dash. So 0 dash it belongs to R dash. So this is the first condition. Since pi of 0 is equals to 0 dash, we have, so 0 belongs to kernel pi. So first we have to verify. First we have to show that kernel pi is non-empty set. So kernel pi is non-empty. So kernel pi is non-empty set is nothing but, so kernel pi contains at least one element. So this kernel pi contains at least one element. So that's why we are taking every identity element in domain can be mapped to identity element in codomain. So pi of 0 is equals to 0 dash. We have 0 belongs to kernel pi. So therefore, so at least one element. So 0 element is belongs to kernel pi. So therefore, kernel pi is non-empty set. Hence, kernel pi is always non-empty. So this is the first condition. We can read this one. Yes. So kernel pi is always non-empty set. Okay. So first we have to show that kernel pi is non-empty because it contains at least one element. So that's why we are taking pi of 0 is equals to 0 bar. Pi of 0 is equals to 0 bar. So therefore 0 belongs to kernel pi. Hence kernel f is non-empty set, always non-empty set, because every zero element is mapping to zero element in codomain. So therefore kernel pi is non-empty. So next let a comma b. So we are taking a comma b belongs to kernel pi. So by using the definition of kernel pi, pi of a is equals to 0, pi of b is equals to 0 dash. So we are taking two elements. A comma b belongs to kernel pi. That implies pi of a is equals to 0 bar, pi of b is equals to 0 bar. And pi of a minus b is equals to pi of a minus pi of b. So this step, a comma b belongs to kernel pi, then pi of a is equals to 0 dash and pi of b is equals to 0 dash. So we are taking two elements. So two elements a comma b or belongs to kernel pi. So kernel pi lo any two elements, we are taking two elements in kernel pi. The image of that element should be mapping to 0. So pi of a is equals to 0 and pi of b is equals to 0 dash. Okay. So the images of a and b are should be 0 dash. Pi of a is equals to 0 and pi of b is equals to 0. And so this is pi of a minus b is equals to pi of a minus pi of b. So this is by using homomorphism condition. Homomorphism, first condition of homomorphism, pi of a plus b equals to pi of a plus pi of b. So this is first condition of homomorphism. So pi of a plus b is equals to pi of a plus pi of b. In place of addition, we are taking subtraction minus pi of a minus b is equals to pi of a minus pi of b. So this condition. So pi of a minus b is equals to pi of a minus pi of b. So but pi of a is equals to 0 dash, pi of b also 0 dash. So this is by using homomorphism condition. Pi of a minus b is equals to pi of a minus pi of b. First condition of homomorphism. So that is equals to pi of a is equals to 0 bar or 0 dash. Pi of b is equals to 0 dash. So therefore 0 minus 0, 0. So finally pi of a minus b is equals to 0. So therefore A minus B belongs to kernel pi. So this is first condition of ideal. So A minus B belongs to kernel pi. So kernel pi is ideal and crucial ante we have to show that A minus B belongs to kernel pi and A into R belongs to kernel pi, R into A belongs to kernel pi. Okay. So we have to show that kernel pi is ideal of R. We have to show that we have to prove that these conditions A minus B belongs to kernel pi, A into R belongs to kernel pi, and R into A also belongs to kernel pi. So these three conditions. First condition A minus B belongs to kernel pi. So this is the first condition of ideal. So therefore A minus B belongs to kernel pi. Also for R belongs to R. R belongs to R. So pi of A into R is equals to, so this is second condition of homomorphism. So second condition of homomorphism, pi of A into B is equals to pi of A into pi of B. So here pi of A into R is equals to pi of A into pi of R. So but pi of A is equals to 0, 0 into pi of R. So total term is 0. So therefore A into R also belongs to kernel pi because the image of A into R should be 0 dash. The image of A into R is equals to 0, and similarly pi of R into A is equals to, so here also we can apply the second condition of homomorphism, pi of R into A is equals to pi of A, pi of R into pi of A. So that is equals to, so but pi of A is equals to 0 dash. So pi of R into 0 dash equals to 0. So therefore A into R and R into A are in kernel pi. So this is the second condition of ideal. So thus kernel pi is ideal of R. So this is the theorem. So this is a very, very important theorem. Statement. Fundamental theorem of homomorphisms of a ring. Statement. Let R and R dash be rings and pi a homomorphism from R into R dash with kernel U. Then phi of R is isomorphic to R by U. So pi of R is isomorphic to R by U. In particular, if pi is an epimorphism, then R dash is isomorphic to R by U. So this is the statement. So pi is defined from R to R dash homomorphism. So pi's homomorphism is nothing but satisfies homomorphism conditions I with kernel U. So kernel U is nothing but, so previous definition of kernel pi is equals to pi of A is equals 0 for all A belongs to R. So then pi of R is isomorphic to R by U. So here isomorphism is nothing but we have to show that pi is 1 1, pi is onto, so pi is homomorphism. So isomorphism is nothing but, so we have to show that 1 1 condition, onto condition, we have to verify 1 1 onto homomorphism. Three conditions. So we have to verify 1 1 condition, onto condition, homomorphism. Okay, na? So this is the isomorphism. So R by U. R by U is nothing but factor ring. In factor ring, every element in factor ring, so cosets form like this. R by U. So this is factor ring or quotient ring. So factor ring lo elements. So A plus U, comma B plus U. A plus U, comma B plus U. So like this, cosets form. A plus U, comma B plus U. So every element in factor group is of the form A plus U, comma B plus U. So where U is ideal. U is ideal. So here U is ideal and R is a ring. Okay? every element in R by U is of the form cosets form, like A plus U comma B plus U comma U plus A comma U plus B. So A comma B R belongs to capital R and U belongs to U. Okay, na? So this is the statement. Proof. Let A belongs to R, then U plus A. So U plus A belongs to R by U. So this is left coset or right coset. So cosets form. Every element in R by U is of the form cosets. U plus A belongs to R by U and pi of A belongs to pi of R. Okay, na? So A belongs to R. So pi of A belongs to pi of A belongs to pi of R. So we define a mapping. Consider a mapping psi function R by U to pi of R. So ఈ మ్యాపింగ్ ఎలా తీసుకోవాలంటే we can define a mapping. So based on question, based on statement of theorem. So like here. So pi of R is isomorphic to R by U. So we define a mapping R by U to we define a mapping R by U to pi of R. Is clear? So psi function R by U to pi of R is given by, so psi of R by U elements is of the form U plus A. We are taking R by U element is of the form U plus A. So psi of R by U element U plus A equals to pi of A element pi of A. Pi of R element is nothing but pi of A. So that is equals to pi of A. Okay, na? So define a mapping psi function R by U to psi of pi of R. Psi function R by U to pi of R is defined by psi of, so element in R by U is of the form U plus A. So U plus A belongs to R by U. So that's why psi of R psi of U plus A equals to, so pi of A belongs to R. So pi of A for all A belongs to R. So this is the mapping. Okay. So now we have to show that this mapping is 1 1 onto and homomorphism. Homomorphism. So then we can say that psi is isomorphic to R by U to pi of R. Is clear? So this is a theorem statement. And also, so before going to prove this theorem, so but our defined mapping is well-defined mapping or not. First, we have to verify psi is well-defined mapping or not. So how to verify a function is 1 1 function. So 1 1 function is nothing but, so I will discuss this theorem in next class. Next class. So but I will explain basics. So like, so what is 1 1 function? So 1 1 function and onto function. So 1 1 function, how to verify a given function is 1 1 function or not? So 1 1 function is nothing but, so pi of f of x
A
is
is
equal
equal
f of phi. So that implies x is equals to
X
y.
is equal to Y.
So this is 1 1 condition. So we have to verify f is 1 1 function or not is nothing but f of x is equals to f of y. So that implies x is equals to y. Then we can say that f is 1 1 function. So onto function is nothing but every element in codomain. Every element in codomain, there is a pre-image in domain. So there is a pre-image in domain. So this is called onto function. And also, so well-defined function. So how to verify a function is well-defined function or not? So well-defined function is nothing but, so 1 1 condition f of x equals to f of y. So that implies x is equals to y. So this is 1 1 condition. So how to verify well-defined function is nothing but we are taking x is equals to y. So we are taking x is equals to y. We have to prove that f of x is equals to f of y. So then we can say that f is well-defined function. So here also, so we are taking psi is a function from r by u to pi of r. So we have to show that size before. We have to show that size well-defined function. Step children. Therefore, the mapping size well-defined function. So we are taking u plus a is equals to u plus b. We have to show that pi of a is equals to pi of b. Like x is equals to y. We are taking x is equals to y. We have to show that f of x is equals to f of y. F of x is equals to f of y. So like x is equals to y is nothing but u plus a is equals to u plus b. So that implies so pi of a is equals to pi of b. F of a is equals to f of b. So this is well-defined function. So next step, so the size isomorphism. So isomorphism is nothing but so first one condition usually. So this is one condition depth one condition. So next,
Onto condition.
so this is onto condition. So size injection clearly size onto condition. So this is onto condition. So next homomorphism conditions. So psi of a plus b is equals to psi of a plus psi of b. So psi of a into b is equals to psi of a into psi of b. So then we can say that so r by u is isomorphic to pi of r. So this is the theorem. I will explain in next class. There is no sufficient time for. ఎవ్రీ సాటర్డే సండే మీకు 12 to 1 ఆల్జిబ్రా క్లాస్ ఉంటుందమ్మా. 3 to 4 ఏమో మీకు అనాలిసిస్ క్లాస్ ఉంటుంది.
Three to four A class, sir.
3 to 4 అనాలిసిస్ క్లాస్ ఉంటుందమ్మా. 12 to 1 ఆల్జిబ్రా క్లాస్ ఉంటుంది.